Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. We're going to jump right into it because today I wanted to get into, want to do two problems from the problem set that we had, and it's going to introduce a new topic. So just really want to get into it so I can explain everything. Let's make sure I can see everybody and the chat. Okay, good. So we're going to go over these two problems. We've been talking about a lot of stuff, but for now we are just going over a lot of problems just to put everything together. I think I've taught you everything about computing probability techniques that I'm going to teach you. So it's at this point, it's just a matter of you going through problem sets. And I think I also have a third problem set here, problem set 3, which is much larger that you guys can go through that I'll have pasted here. I might do problem 16 for you guys, just as an extra example of something I want to introduce today, but it's only if time permits. But there's a lot more there. So we have 3 probability problem sets. They should be on the website. And I did most of the examples from set 1, a good chunk of the examples from set 2. I might have done everyone from set 1, I don't remember. But and then I'm going to give you set 3, where you guys are going to go through this and work on them. So you'll have a lot of practice, because probability can be a very weird topic. So the more you practice, the better. But for now, just want to get through these two. Teach you the last thing I want to teach you about finding probabilities. And we're not exactly finished with probability, because I'm going to tell you guys about things like probability distributions and expected value, which is going to be tomorrow. And then we can slip into some basics about statistics. We're not going to go far into that, of course. But yeah, that's the plan. So let's actually jump into it. So here's so problem 6 is not anything that's going to be that we need any new material for. That's something that we can do right now based on what we already know. So let's actually do that. Business majors, you guys, you're required to take Math 1108 and Math 1109. So Math 1108 is what you're currently doing. 1109 is the calculus for business majors. But suppose on average, 15% of students get A's in Math 1108. Just a made up number, don't panic. While 10% get an A in 1109, right? And suppose we also know from statistics, which we'll talk about, 23.5% of students get an A in one course or the other. So let's say you know this information. Question 1. Someone's coming in here. What is the probability that, well, it asks for what fraction of students, but it's the same as asking for the probability. What fraction of students get an A in both courses? So let's do something here. Let X equals the event student gets A in Math 1108. Y equals the event. So of course, we know one of the first things we want to do with a probability problem is just to set up our events, our variables. Math 1109. So in A, what do we want? What is it part A is asking us? Probability of what?
X and Y.
X and Y. Okay, so now that you know that, right? So you set up your variables, then figure out what are you looking for, right? You need to kind of know that in order to find it. Otherwise, you may never find it, or you might find it and not even know you have it and try to do something else, which also happens sometimes. How would I find that based on the information I have here? What do I know here? We should put that in as well. What are we given? We know 15% of students get an A in 1108. So the probability of X occurring is 15%. We know the probability of Y occurring, 10%. And what do we know? 23.5% get an A in one course or the other, which means we know the probability of X or Y. And this is 23.5. Okay, so given that information, how can you find and? Anyone? Bueller? Don't have to tell me the answer, just tell me like how you would go about it. You know each individually and you know the or probability. How do you find the and probability?
The inclusion and exclusion principle.
Well, yes, we use the inclusion exclusion principle to prove the thing that we use to find it. So you're on the right track, but you're not quite there yet. The inclusion exclusion principle is only about the sizes of sets, but that did help us determine the formula. So what is called is the law of disjunction, which we proved using the inclusion exclusion principle. So that would tell you that the probability of X or Y is the probability of X plus the probability of Y minus the probability of X and Y, which means you can find the probability of X and Y by just solving for that in this formula. Bring it to the left side and then bring the or to the right side. And we know each of these. So probability of X is 0.15. Probability of Y is 0.1. And probability of this is 0.235. Right, so that's 0.25 minus 0.235, which is 0.015. Okay, so that's the proportion of students. If you want to, so that's fine. Or you can say it's 15 out of 1,000 students will get an A in both. That's the fraction of students. So throwback there. Like, I think the first day we started using formulas for probability, we learned that formula. It's a very important formula. Don't forget it. Let's move on to B. What is the probability that a student gets A in Math 1108 will get an A in Math 1109? Okay, what is that looking for? Probably that a student who gets an A in 1108 will get an A in 1109.
Prediction. No.
Condition? What's the condition?
The student gets an A in Math 1108.
Yeah, but tell me, like in terms of these symbols, what are we looking for? Probability of what? Right, so you think it's a conditional probability. It's probably of A given B. Like who's the A, who's the B? In terms of these new variables here. I didn't want to use A and B because in the question it's about getting an A. I didn't want to mix up the grade A with the event. Yeah, John?
Probability of y given x.
That's right, probability of Y given X. Interpreting is like half the problem. Like once you can interpret the question, like what the heck is this asking me? Then it's a matter of, oh, I have a formula for that, right? So once you can know, okay, that's what I'm looking for, then you can realize, oh yeah, there's this thing called Bayes' rule. There's this other thing called law of disjunction. There's this thing called and probability when they're independent. There's the, you have all these formulas that you can use, but you have to, of course, interpret the problem first. For that, you set up your variables. Write down what your given probabilities are, and then you can know what formula you can use based on what you have. So we want that. Given that they got an A in Math 1108, which is X, so that's what occurred first. What is the probability that Y will occur? And that is that they get an A in Math 1109. So now we know probability of Y given X is the probability of X and Y divided by the probability of X, right? X and Y we found just now, so that's 0.015. Probability of X is 0.15. So that's going to be what? Is that 0.1? Yeah, it's 0.1. So there's a 10% chance that if a student got an A in 1108, that they will get an A in 1109, according to these makey up numbers. All right, what about C? Is getting an A in Math 1108 independent of getting an A in Math 1109? Okay, what do you guys think?
I think they are.
Why?
Because, the independent rules for independent events said that probability of A given B equals probability of A, and we just found that probability of Y giving X is equal to the probability of Y.
Right, probability of Y given X, we found that that's 0.1, but we also have probability of Y is 0.1. So probability of y given x is equal to the probability of y. So given that x happened, doesn't really matter. Y is going to happen with the same probability. X happening did not affect y happening at all. So yes, they are independent. Okay, good. Now, you do have another option, or you could notice that if you took the probability of x times the probability of y, you would get 0.15 times 0.1. That would give you 0.015, and that was the probability of x and y we found up here. And so you would see that the probability of and is the product of probabilities. And so you would get x and y are independent that way. D, bonus. Are x and y mutually exclusive? What do you think? Yes, no, maybe so.
No, because the probability of x and y would have to be 0.
Right. So you have the probability of x and y. We found that is 0.015, but that's not equal to 0. So no, they are not mutually exclusive. So remember what mutually exclusive means. Mutually exclusive is asking, is the probability of x and y equal to 0? If they cannot occur at the same time, that's what it means to be mutually exclusive. So remember that. All right, cool. That was a nice little refresher of some important concepts that I'm definitely going to test you on in various scenarios. And I might even make the word problem suggest an answer that is the opposite of the answer, or it might suggest something that makes sense. In this case, it kind of makes sense. Like how well you do in this class actually doesn't, I don't think it affects what you, how you do in 1109 at all, really. Studying calculus is very different from what we're doing. It's a different mindset. Need different skills. But yeah, all right, cool. So the real main example that I want to talk about is this guy, because he's going to allow me to introduce a new topic. So let's suppose you have a basketball player that you know makes 70% of the free throws that he attempts, right? And suppose he takes 10 free throws and the outcomes are all independent, right? So if he misses, he doesn't just, his performance goes down. And if he gets it, he doesn't like get all full of himself. And yeah, so he's just going, every shot is independent. what is the probability that he will make all 10? Or what is the probability that he will make exactly 2 out of the 10? What is the probability that he'll make between 3 and 5 of these shots, or make at least 1, right? So we have this guy who his success rate for free throws is like 70%. And we just want to know the probabilities that if he takes 10, how much can we expect him to get really? So in each of these scenarios. Okay. Now, I want to kind of illustrate this idea by first going through a smaller problem, which is actually a technique that you can use on an exam. So, or just in general, I guess. So if you want to solve a problem and the numbers are too large, as you will see that if you try to do this directly, you'll recognize that the numbers are going to be huge. You can start by doing a smaller problem. So that's what I want to do here first. Let's, that's fine. Let's do a smaller subproblem first. Suppose he is only making 3 free throws. So let's not go all the way up to 10. What is the probability he makes 2? Okay. So we're going to figure this out, and it's going to lead us into the way that we're going to want to attack that problem, because you're going to realize very quickly if you attack that directly based on what I told you so far, it's going to be a while. So how, knowing that he makes each throw independently, how would you find the probability that he makes 2? What is the probability that he makes 2? Like how can you do that?
Could you explain your question?
Yeah, he's making 3 free throws. How would you go about finding the probability that he will make 2 of them? Like, how do you even start that problem? What would you think? Well, maybe you want to start talking about, well, how can he make 2? Tell me about that. Tell me about the scenarios. Like, what is one way that he can make 2?
You can make the first one and the second one. You can make
Right.
the first.
So you
first
have these stages. You have the first, the second, the third attempt, and he can make this one and this one, but miss that one. Right?
Yeah.
What is the probability that that will occur?
67%? Or, oh, isn't it a 1/3 chance? Because there are 3 different, I guess, sets.
No, don't forget about probability. It's not just like you're randomly choosing something. That's a part of it, but to get that check, right, has a probability attached to it. What is the probability of getting that green check?
49.
Huh?
49%.
Why 49%?
Uh,
Of the green
One-
check?
yeah.
To get a green check, how do you get 49? So what I'm saying is the check means he makes the shot. And the X means he misses the shot. Right? What is the probability of him making the shot is what I'm asking.
Wouldn't it be 70%?
It'd be 70%, be 0.7. Okay, so he makes the first one, he makes the second one, he misses the third one. And these are all independent events. What is the probability of these this scenario occurring? And the fact that they are independent is something that can help us here. So notice for another way we can phrase this scenario is that he makes the first, and then he makes the second, and then he misses the third. So if we have independent events, and I know that's what I'm looking for, how can I find the probability?
Would it be 0.7 times 0.7 times 0.3?
Right, you multiply them because it's independent, right? So it's 0.7 times 0.7 times 0.3, right? Which is 1 minus 0.7, right? It's the opposite. So in other words, that is 0.7 squared times 0.3. That's the probability of that happening. Now, of course, that's not the only way he could make 3 shots, right? There are other scenarios. So he could actually also, he could make the first, miss the second, and make the third. That's another way to get 3, right? And so what's that probability? Well, if they're independent, you just multiply them, right? So you'd have 0.7 times 0.3 times 0.7, right? And that also gives you 0.7 squared times 0.3. Are there any other ways he can make 3? Well, yeah, right? He can miss the first. This point, he's getting all down on himself, having flashbacks to a childhood when people tell him, you never make, you're gonna amount to nothing. You're never gonna be anything. You know, he's getting all in his head. He's like all upset. You know, he's just like, man, I'm so horrible. I just suck. Then a voice comes out in the stands. We believe in you. And he suddenly gets the courage and he's like, ah, ah. You know, he's like really loud, very epic music. And then he can make the last 2, right? So that's one way that can happen. The last one was very dramatic. But now if you look at that in terms of probability, That just means, oh, he got a 0.3 and then he got 2 0.7s. Right? There was a 30% chance that he would have missed it, and then 70% chances that he would make it on the other one. But you'll notice that that's actually the same thing. Now you'd also notice that this accounts for all possible ways that he could make 3, right? So this here is all possible ways to make 2 out of the 3. Okay, so now here's the important part. What do we do with all these numbers? Now that we have that, what do we do with them? So we could make 2 out of 3 the first way, or the second way, or the third way. What does that tell you? So he could make 2 this way. So can make 2 out of 3 this way, or this way.
There's 3 ways. So
Yeah. So what do we do with that?
It's like choose 2 from 3.
You choose 2 from 3. What is that?
2
3 choose 2 would be what?
like you need to shot into.
Yeah, but that number 3 choose 2. If I were to ask you what is that number, what would you say? Like what is the interpretation here?
Permutation?
That's not a permutation, that's a combination.
Oh yeah.
Notice this is that was a question I was going to eventually get to, but since you already answered it, let's just deal with it now. Notice this, there are 3 choose 2 is actually the number of ways that this could occur. Right? Out of 3 free throws, choose the 2 for him to get success on, right? So that actually tells you the number of ways that he could actually achieve this outcome by me just randomly picking when the success will happen. Well, not random, like me counting all possible ways that this number of successes can happen. And okay, so that's what the choices would be. That was going to be what I was going to eventually ask. Because that's important, because now if there were like 10, which going back to our problem, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I ask you, how many ways can you make 2 free throws? That's going to be, come on, what do you want from me? Right? That could be like this and this, or it could be this and that, or it could be this and that, or it could be this and this, or it could be this and that, or there's going to be so many, like if you try to directly count how many ways, it's going to take forever. But once you realize, oh, there are 10 spots, I just want to choose 2 of them to have the success in, then it's easy. You realize it's just a combination, right? So that's where I'm getting at. So that's why you can see with the smaller numbers, you can kind of see the pattern a little bit nicer. Now, what about this part over here? What does this mean? I can get the free throws this way or that way or that way. What would I do with that information? Note, these are, how do you describe these three different events? I mean, we're running out of time, so allow me to lead the witness, Your Honor. I don't think you can have Your Honor allow you to do something that you're not supposed to do, but whatever. It's my rules, my class. Could these occur at the same time? Could he make the first and the second and simultaneously make the first and the third? No, both of these situations cannot occur at the same time. Because if he makes the first and the second and the first and the third, well, that kind of means he makes all three. He wouldn't have made two, right? So these cannot occur together, but they do represent different ways for him to achieve the result. So there's an OR here and they're exclusive. So what does that tell you? What can you do with these numbers? Something we've seen before. So they can occur together. So that's what we call mutually exclusive. And when events are mutually exclusive, what can we do with their probabilities in terms of OR?
You can add them.
You can add the probabilities. Now, what I do want you to notice is that we're adding the same thing. So if you add these, you would get 0.7 squared times 0.3, but you're going to add it a certain number of times. Namely, you're going to add it to itself 3 choose 2 times. That's kind of weird, oddly written. That's what I want you to kind of realize what we're getting at here. If you know the number of successes in this kind of scenario, you can just take the number of successes, the probability of success, multiply it by the number of times you want the success. Then you're going to have the probability of failure. You're going to actually multiply that by the amount of times he would have failure. And then you would just add them together about how many possible ways could he get that number of successes and failures, which if you start counting it, you realize that's just a combination, right? So you'll notice here, this is a 1, and I want you to realize these numbers. So this is 3 choose 2, number of ways to get 2 successes and 3 failures and 1 failure, because you mean. So yes, 2 is the number of checks that he would get, and 1 is the number of X's that he would get. And notice that the number of successes is the guy here that you're choosing. And I also want you to note that the 3 is the number of attempts, or as we might call them, trials. Okay, so what this gives us is it turns out that this kind of scenario can happen quite often. It's called something called binomial probability. So binomial, the word bi in there, of course, means that it can go 2 ways. And the ways that we're talking about here is success and failure. So there are a lot of times when you have a situation where there are really only 2 types of outcomes that you care about. Did we achieve a certain result or did we not, right? Yes or no, right? On or off, yes or no. Did we get it or did we not get it, right? And that leads to something called binomial probabilities in a very specific situation. Suppose we're repeating an experiment n times. Right? And we have these 3 conditions. 1, each trial is independent. 2, there are only 2 types of outcomes. Success or failure. And probability of this equals P, and the probability of this equals Q, which is 1 minus P, right? So, of course, let me put this as a condition. The same experiment is repeated n times. You're repeating the same thing. Each time is independent, and there are only 2 possible outcomes. Let x equals the number of successes. Then we have the following: the probability that the number of successes is equal to a certain number, k, the number of successes that we're looking for. So in the above example, n was 3 and k is 2. It's going to be n choose k, p to the k. So you're going to choose out of the n times the k parts, the k times where you're going to have the successes. That's going to just be you multiplying the probability of success k times. And then obviously the rest of the times you'll have failures. So that's just going to leave you with n minus k, which you'll realize is what we have up here with the 1 power. It's 3 minus 2. So that's called a binomial probability. And we'll talk about it a little bit more next time. But just to kind of quickly go through this, it turns out that once we know that, the rest is not going to be bad. So now we can go back to this problem. You'll notice here, we have n equals 10 trials. He's making 10 free throws. We also have the probability of success is 0.7. We know that the probability of failure is 0.3. And we have independence. So this means it's binomial. So he's doing the same thing. He's just taking free throws. Only two outcomes. He can make it or he misses it. That's the probability of doing either. And each one is independent. So if we let x equals the number of successful throws, then what you'd realize part A is asking is the probability that he makes all 10. Well, that's going to be the probability that x equals 10, which is going to be here, 10 choose 10, p to the 10, q to the 10 minus 10. You'll notice that equals 0.7 raised to the 10, which makes sense for other reasons, right? 10 times in a row, he makes it 70% each time. You just multiply the probabilities. So makes sense by independence. You'll just multiply the probabilities. So you didn't even need binomial for this, but since we already set it up, we can use it. Part B is a little bit more complicated, makes exactly 2. Now this is where you'd really need the probability. You want x equals 2. Well, how many ways can that happen? Well, it's 10 choose 2, p to the 2, q to the 10 minus 2, or it's going to be right, you can plug into your calculator, but we'll do that another time. If you look at C, makes between 3 and 5. C is really asking the probability that x is between 3 and 5. But this really means that the probability of x equals 3, or the probability of x equals 4, or the probability that x equals 5. Because this is or, and these are mutually exclusive. So this would be 10 choose 3, 0.7 to the 3, 0.3 to the 7, plus 10 choose 4, 0.7 to the 4, 0.3 to the 6, plus 10 choose 5, 0.7 to the 5, 0.3 to the 5. And then you add those up. Makes at least 1. This means x should be greater than or equal to 1. Of course, that is going to mean the probability of 1 plus the probability of 2 plus that, which is a lot. So I would use the complement. This is 1 minus the probability that x equals 0. So it's 1 minus 10 choose 0. He misses all of them, 0.7 to the 0, 0.3 to the 10 minus 0. So that is a binomial probability type, which you can try this for next time. This is a nice exam type problem, by the way. I have put this problem on an exam before. Obviously, I'm not going to do it for you guys now, but I'd want you to try this. And I will leave it in the notes, which you guys all have the link to. But we have to go. So this is the last technique for finding probabilities that you would need to know. And it works in this very specific circumstance. You're repeating something n times, they're all independent, and there are only 2 possible outcomes. This is a binomial probability, which is a very common thing, believe it or not. Yeah. Here's a really interesting question, final type problem for you guys to try for next time. We'll stop there. Yeah, so thank you for your time and attention. We'll wrap this up tomorrow, probability, maybe even start some statistics. And that's it for now. Have a good day. Work on your outlines. If you haven't set a meeting with me, I think there are more slots available today, so do that. And I will see you guys on the next one. Ciao.